Namaskara. In this session we continue our discussions on divide and conquer algorithms. In the two case studies that we have seen so far, we have split the problem into two subproblems. That is a basic form. Both merge sort as well as the min max problem has split into two subproblems. Sometimes it will be more convenient, and in fact it is more natural to relate the solution of the given problem to several smaller subproblems. It is a recursive program. Divide and conquer is a recursive program. So more than two subproblems might be involved. So we are going to look at one such general case and then give a canonical example for this. This is Karastuba's algorithm for multiplying two n-bit numbers. Okay. This has again very interesting historical background. Kolmogorov, who is a pioneer in formal or foundations of probability theory and in various subjects, is one of the pioneering researcher, and he will often give various in various international conferences challenging problems, and he is almost convinced that if you want to multiply two n-bit numbers, of course he was using the digits, but I am putting it across in terms of bits. Let us say you have A1, A2, An is an n-bit number, and you have to multiply with another n-bit number B1, B2, Bn. Like in our high school method on our decimal digits, if you are looking to multiply 786 with 439, something like this, you multiply digit by digit. Okay. So first let us say you write 786 and 4. First you multiply by 9 and then multiply by 3 and then multiply by 4. The high school method, very simple, digit by digit you multiply and add all the individual digits. Okay. Because we are working on a positioning number system, we are shifting it, it is equivalent to the presence of 0. Basically we are multiplying first by 9, then multiplying by 30, then multiplying by 400, adding all of them. To represent that we are multiplying by 400, we ignore the zeros and then simply right shift it, left shift it and then write the numbers. You could have kept the zeros and then you can write in an aligned way, but that is not necessary because adding with zeros you get the same number. So you are going to generate in this way n square digit multiplication and n square additions. So individually you have to multiply the digits and the results are to be added. So n square is the labor for that. They are all independent digits, they are not related in any manner. An arbitrary number has got independent digit. So how will you multiply two arbitrary numbers? They are highly independent, so there is no relation between them. So you have to multiply each digit with each other digit. Looks like there is no shortcut possible, and there may not be a way to save the number of digit operations to compute the product of two numbers. In our context, the number of bit operations, can this be reduced further from n square? can you significantly reduce this below n square? This question Kolmogorov used to pose in various conferences, workshops, meetings, because this is a very challenging one. It appears that there is no way this can be reduced because each bit is independent and you can't skip anything. You have to multiply all of them, and that shows that we may have to perform n square bit operations. And Karastuba, who was a postgraduate and who was listening to one of these lectures, he found this problem to be interesting, and then finally he found out a divide and conquer method, and to the surprise of everyone, he showed a solution which is significantly smaller in order than n square. Okay? And that has really surprised the world. It is one of the very surprising results when this was proposed, because everybody thought that there is no shortcut possible to the high school method where every bit is multiplied with every other bit and therefore n square complexity is the minimum. But then Karastuba has surprised the world by presenting a divide and conquer algorithm, and he made one very clever move. Okay, we will take a closer look at his method, and then we will also see some interesting analysis, little more mathematics we will do while doing the analysis of his algorithm. So we have a master theorem, it is well known, and then you might have done that in your basic course on algorithms. T of an is a times T of n by b plus n power d. You have a subproblems, each of size n by b. The one that we have seen in merge sort all, we have seen two subproblems of size n by 2. So a and b are 2 in all the cases that we have seen. That need not be the case. A can be a different number, b can be a different number. N power d is the total cost, anything other than the recursive calls. For example, for splitting you might have taken some operations, combining you might have all put together, anything other than the recursive calls in the code. Okay. And base case is trivial, we just assume that T of 1 is some constant C. Here we may use an upper bound and we may use some constant there. Just to avoid the clutter on the screen, I am using only n power d. You could have used some constant C there and another C dash here, and they are not necessary. This kind of recurrences can be solved conveniently when n is a power of b. Okay. Again, there is an infinite sequence b, b square, b power k. So when n is of the form b power k, we have appropriate algebra done, and you can get T of n in some closed form, in some simple form. Okay. But we know if we are able to solve for an infinite series and if we could prove some monotonicity, then that will fix for all n. Therefore, we will in general take advantage of the kind of results available in our favor. Monotonicity can help, and there are several other conditions that will also help in extending the solution of this recurrence equation for specific values. Here the specific values are powers of b, that is because you have n by b over here. Only for powers of b, n by b will be an integer, and recursively it will continue to be an integer. So we normally assume that n is a power of b and then derive results. This is well known, so I will summarize the result. Then T of n is equal to order n power d if A is less than b power d. If A is less than b power d, and this is equal to order n power d log n if A equals b power d. If A equals b power d. The other case is order n power log A to the base b if A is greater than b power d. So let me summarize, it is getting crammed here. T of n is order n power d if A is less than b power d. So value A and b power d, they are compared. Another way of saying is log A to the base b is less than d. Another equivalent way of saying A is less than b and is equal to order n power d log n if A equals b power d equals order n power log A to the base b if A is greater than b power d. So this is the case when log A to the base b is actually equal to d. This is the case where log A to the base b is greater than d. So if log A to the base b and how it is related to d, depending on that you are getting the value of T of n. This is called master theorem, this is well known, all elementary course on algorithm will discuss this, and then we fit various values of a, b and d that we get in our algorithm. So we will design an algorithm, and in our algorithm what would be a, b and d, accordingly we plug in those values and get the T of n in closed form. Therefore we will use this to indicate, we do not have to every time do the algebra to derive the solution. Once for all, for the general case the algebra was done, and then we have this master theorem. There are several master theorems. We are going to see some more complex master theorems later. It's a very simple one. Okay. And what Karastuba has done is the following. First he has come up with a divide and conquer algorithm that works as follows. Call the first number as a and split into a1 to an by 2, an by 2 plus 1 to an. Split the first number into two parts roughly equal. So basically it will be floor n by 2 and ceil n by 2, but floor and ceil I will ignore, I will write only as. And b is again b1 to b n by 2 and b n by 2 plus 1 to bn. I write a as a1 to an by 2 0 0 0 0 plus a n by 2 plus 1 to an. In other words, I am interpreting this a as, if you call this as a1, if you call this as a2 and b1 and b2, A can be written as A1 2 power n by 2 plus A2, and B can be similarly written as B1 2 power n by 2 plus B2. Therefore, AB can be written as A1 B1 2 to the power n plus A1 B2 plus A2 B1 2 power n by 2 plus A2 B2. So, the product can be, this is the product of two n bit numbers, this is the product of two n bit numbers. This is the product of two n by 2 bit numbers. Because A1 is the first half of A, A2 is the second half of A. Similarly, B1 is the first half of B, B2 is the second half. Their size is n by 2. Therefore, when you are saying A1 B1, you are actually multiplying two n bit numbers. Same, all these things are n by 2 bit number. So, you can do the following, you can evaluate A1 B1, you can evaluate A1 B2, A2 B1, A2 B2, because you are given A and B. First half and second half you consider and you can evaluate it. How do you evaluate it? Recursively, right. Therefore, what I have to do is, I have to perform these 4 multiplications and plug in those values. I must have A1 B1, A1 B2, A2 B1, A2 B2. There are 4 multiplications. Of n by 2 bit numbers. Four multiplication and then combining cost. That is very simple. This is a 2 n bit number, this is all added only order n, maybe 6 n, 5 n. Therefore, T of n equals 4 times T of n by 2 plus, let us say, order n. It is order n. Therefore, this is a very straightforward divide and conquer. Split the first number into 2 parts, second number into 2 parts. The product is nothing but this one. If you want to evaluate, you get these numbers, and these are only shift operation, right. They are just shift operation, very easy to achieve. You do not have to do multiplication with the 2 power n. Appropriate number of shift. So, it is all order n. Okay. So, after performing these 4 multiplication, you do further order n computation and you have final answer obtained. Therefore, T of n is 4 times T of n by 2 plus order n is the solution. What is the complexity of it? Here A equals 4, B equals 2 and D equals 1. Therefore, A is greater than B power D. Hence, the third case, therefore, T of n equal to order n power log A to the base B, 4 to the base 2, that is equal to order n square. You have come up with a divide and conquer algorithm, split the input into 2 parts, then evaluated the product. Product has got several sub expressions. You have to evaluate all the sub expressions, then put together. All of them have the same complexity as your naive method. same order. This is much more complex. Why would I need a more complex order n square algorithm? I do not get any benefit, right. The earlier one is a very simple n square algorithm. Digit by digit you do and then solve. But this one is much more complex, and but still it is only n square. That shows you should not apply an idea in a naive or a direct way. It is important that you see what are the ways in which we can improve. Here you can't split the problem with size anything smaller than 2. A is split into 2 parts, B is split into 2 parts, right. So minimum 2. If at all you can have more, it's a problem. But if you look into the number of subproblems, there are 4. There are 4 multiplications of, this is one n by 2 bit multiplication, yet another one and yet another one. Therefore, there are 4 subproblems of size, and that is the reason why you get this. Therefore, the natural way to think to improve the complexity is reduce the number of subproblems. If A can be reduced, I am going to get a more efficient solution. That is what Karastuba has achieved. What he has achieved is very impressive, right. What he has achieved is that with 3 multiplications he could solve it, n by 2 by n by 2 bit multiplication. It was not 4, it was 3. So if it were 3, then A equals 3, B equals 2, D equals 1, still A is greater than B power D, that is because 3 is greater than 2. Therefore, the solution is order n power log A to the base B is nothing but order n power log 3 to the base 2. This is 1.56 kind of a thing. Therefore, this much better than order n square. So the moment he started focusing on the number of subproblems, he came up with an ingenious solution. He saw certain dependencies, and based on that he could reduce the complexity. Okay. So you have to calculate 3 values. X1 is A1 B1, X2 is A1 B2 plus A2 B1, X3 is A2 B2. These 3 quantities you have to calculate, and when you calculate this, after that shift and addition you have to do to get the final answer, right. What is the final answer? AB is x1 times 2 power n plus x2 times 2 power n by 2 plus x3 times plus x3, that is it. All these things can be done by shift operation and bit addition, which are of order n length. Therefore, I can solve the problem the moment I have these values. This, when I solve recursively, it is getting complex. We are going to still solve it, but we are going to get these values in a slightly different way. I will have x1 and x3 done, they are independent computation of disjoint part, but here is a mix. This can be found out with one multiplication as follows. Find out A1 plus A2 multiplied with B1 plus B2. Theoretically, this is A1 B1 plus A1 B2 plus A2 B1 plus A2 B2. So, if you want this alone, from this product you subtract this, but that is a subtraction. But I am able to get this value with one multiplication and some addition and subtraction, but that is linear. You have this is an n bit number, this is another n bit number. You subtract from this product, you get the answer. That is order n. Okay. But this is the third multiplication. So, call this as multiplication 1, call this as multiplication 2, call this as multiplication 3. With 3 multiplication you have 3 values, okay, m1, m2, m3. You want x1, x2, x3, x1 equal to m1, x3 equal to m3, but what about x2? x2 is you call that A1 B1, A2 B2, okay. Multiplication is A1 plus A2 times B1 plus B2, and x2 is going to be m3 minus m1 minus m2, okay. x3 is m2 here, x3 is m2. Therefore, I am able to get x1, x2, x3 with only 3 multiplications done and some linear cost, that is in order n anyway. Therefore, I am going to have the complexity something like T of n is equal to T of 3 times T of n by 2 plus n, order n. And we have seen that this has a complexity order n power 1.56. Okay. So, this is a more efficient solution. The clever trick is this one: you use only 3 multiplication and get all the values that you want. Earlier, in order to get the values that you want, you have to perform 4 multiplication, but now you are doing only 3 multiplication. And this is Karastuba's algorithm. We are going to make one small observation and then notice that A1 and A2 are n by 2 bit number, but when you add you get n by 2 plus 1 bit number. These are n by 2 bit number multiplication, but this is n by 2 plus 1 bit number multiplication. Therefore, actually it is like this: T of n is less than or equal to 3 times 3 of n by 2 plus 1, because the problem says plus order n. If T of n is less than or equal to 3 times T of n by 2 plus order n, I can easily solve. I can apply the master theorem, but it is something like this. How do we handle that? Okay. We have to come up with a different infinite series and handle this. If it is like this, you can write immediately the solution, order of n power log 3 to the base 2, which is order n power 1.56 ish. But it is actually like this. Well, it will not change the order, but you can see that this requires a different treatment. I can't apply the master theorem. The important thing is that I am getting n by 2 plus 1 rather than n by 2. Okay. How do we handle this? How do you do the analysis for this? Very simple, and except that you have to consider a slightly different infinite series and then solve it. We will see the solution in our next session. Thank you.